Newton's, excuse me, Newton's universal law of gravity here near the end as well. Okay, so yeah, we'll try to make this quick, but yeah. Okay, let's go. Okay, a flat line on a position versus time. So when you see these questions about the slope on a graph, I always just take a time and kind of maybe even sketch the graph out a little bit. Just remember change in y divided by x. So if your change in position is 0, if you stay in the same place, then your velocity will be 0. So yes, this is asking you about the slope. The slope. Unbalanced forces, that would mean that you change the velocity of an object if unbalanced forces are applied to it. Number 3, really the key there, it wasn't really a math problem, it was just looking for, did you recognize the correct unit for time there? Now, also on your exam, when you do have these little kind of one-step story problems built into the multiple choice, I'll go ahead and include an equation there. Which certainly should help you with this as you're working through those little one-step problems. All right, and in fact, yeah, okay. So yeah, we talked a lot about those in class. So I'll kind of, if you have questions about the multiple choice, I will kind of let you approach me on those. But yeah, really, both practice finals had a similar set of multiple choice. And I really think if you understand these multiple choice, you'll be in good shape for the final exam multiple choice. All right. All right, let's look at, while we have a minute here, I do want to also talk a little bit about Newton's law of gravity. So here's the universal law of gravity. Now, a key thing to keep in mind is there is a difference between the words mass and the words weight. Okay, so mass in this equation, m1, m2 are mass. Now the Fg here, this force due to gravity, is what we would experience as weight. So, all right. So as you look at this, Newton's law of gravity, so this big G, it's just a constant, it's just a number, it's very tiny, it's somewhere on the order of like 10 to the minus 19th. Kind of depends what units you want to use to measure the weight. So here I just took pounds. It's kind of an easy one. Obviously we know that, you know, the scientific unit for weight are newtons, but let's just look at it in pounds. So here on Earth, I don't know, I'm about maybe 180 pounds. And so if you want to look at, we could plug in or substitute in the mass of the Earth, which, what would that be? So the mass of the Earth, it's a giant number. It's nothing, it's kind of, in some ways it is a little bit incomprehensible to try to think about. But yeah, the mass of the Earth, where is that? I thought I wrote that down. No, okay. There it is, sorry. So here's the mass of the Earth, and you can see some of these other planets here. But yes, so Earth, then the next most massive terrestrial planet would be Venus. Then really Mercury and Mars are really close in size or in mass as well. So when you think of mass, m, in these equations, m is indeed the mass. Think of that as like the number of atoms something is made of. Okay, so back to the equation. You could plug in the Earth's mass, you could plug in my mass, divide that by the distance squared between me and the Earth, and you could arrive at my weight here, my weight. Now if I went to a smaller planet, Venus is close but slightly smaller, I would weigh 163. If I went to Mercury or Mars, I would weigh even less. And once again, you can play that same kind of game with the gas planets. You know, if I were to stand on Jupiter, which has a much, much larger mass, I would weigh like 450 pounds. Saturn, even though it's a lot more volume, a lot bigger than Earth, its actual mass isn't much different. Neptune, a little bit more massive than Earth. And then Pluto's pretty tiny. I think if I were to stand on Pluto, I would only weigh about 12 pounds. So looking at that, if you if you increase the numerator, you will increase the weight. Now, the same thing, if you increase the denominator, increase this distance between yourself and that planet, an increase in the denominator will make you get a smaller answer for weight. So some of those questions like how would you feel, or how much weight, why would you feel less weight if you're on board the space station, for example? Well, that's because if you're on board the space station, your distance, your denominator there, is going to be larger, which would give you a smaller answer, smaller value for f of g. All right. Now, the other thing I wanted to kind of remind you of with that is, sorry. All right, here we go. So Newton's law of gravity, we didn't really do calculations with it, but I want you to understand the relationships between all of those numbers and all those variables. Now, we've certainly have done a lot of calculations with this equation, F equals ma. Now, if you plug in acceleration due to gravity, then your force would also be, since it's a vector, it would also be force due to gravity. So a lot of times when you look up these accelerations due to gravity on other planets, it's actually listed as a force to mass ratio. So if you look at some of these accelerations due to gravity of some of the planets here. So, we said that on Mars, on Mars and Mercury, there's smaller planets where you wouldn't weigh as much. This is the force to mass ratio for Mars, the weight to mass ratio for Mercury. 9.8, that's our weight or force to mass ratio here on Earth. Now, really, once again, kind of due to our F equals ma, we think of the acceleration as meters per second every second. But that, once again, is the same thing as the force to mass ratio. And then we know on Earth, we usually, for our story problems, we've been rounding this to 10, but still kind of the same idea there. So, so Newton's law of gravity. I kind of think back to that quiz before Thanksgiving, is where I had a page or two on those kind of questions, and so that might be worth going back over and reviewing. Coefficient of friction, it's a ratio. So as things get heavier, the normal force would increase, but that also would increase the force of friction. So that's why we really say the mu, the coefficient, this ratio, does stay constant. Know our units, just keep practicing those. This one here is pretty straightforward, 19. Looking at 20, once again, just think about what is the definition of slope. It's change in y over change in x. So I just take the time to divide them out, and then I really think about what units are going to be used to make those measurements. And then it's easy to think about what units or what the resulting slope would represent. Remember these kind of matching problems, be able to play the F equals ma game. So force is mass times acceleration. Mass is kilograms, acceleration meters per second per second. Now remember weight is force due to gravity. So weight and force have the same units. If I ask you for acceleration, that's the force to mass ratio, and then mass would be the force divided by the acceleration. Force in newtons divided by the acceleration. All right. So on these story problems, keep in mind that if you're going to do a story problem with velocity, acceleration, or force, those measurements are considered vectors, where both magnitude and direction are implied in the way we express those values. Motion graphs. All right. Cart does not move. See how this goes for us. Okay. Yes, just the flat line on your position time graph. Now, the whole thing with these motion graphs is once you've established the position versus time graph, just think in terms of slope. So the slope of this line is 0. The slope of that line is 0. Okay, so car moves at constant velocity. This is our very first day of school. This was a very simple graph. The car just kind of moved away from us. All of our marks were pretty evenly spaced out in the hall. The distance, the change in position for the car was pretty consistent over time. So this is a positive slope, which it's not changing, but it's a positive slope. Here's my positive velocity. It's not changing. This slope here at g, the slope is 0. So my acceleration is 0. Car rolls down the ramp, so really anything moving in response to gravity. This was like our big blue marble graph. I like to think of A and D kind of look, this is just something moving away from us at constant speed. This is something moving away from you, but it starts to pick up a little bit more distance, starts to change its position a little bit more steeply, a little more severely at that last little increment of time. So this we consider to be a changing slope. The slope is becoming more and more and more positive. So, and then I look at this velocity versus time. That's a positive slope. That is a positive value for acceleration that doesn't change. Throw the ball up and down. Up is positive. So if up's positive, think to yourself, acceleration due to gravity should be negative. So here, this was, again, given the choices, maybe this was an easy graph to match because it's the only one that has something moving in two directions. This slope is changing as well. The slope starts positive. Up at the top, up at the peak, it's a 0 slope, a 0 velocity. And then to finish up, it's a negative slope, which finishes up with a negative value for velocity. And this line H is a negative slope, so we get a negative acceleration. That's not changing. All right. Okay, for the graph interpretation pieces, tried to emphasize this in class a little bit, but my best advice is please, please, please take the time to look at what the graph is, what the title of the graph is, what the axes are. Because you'll be looking at position time graphs and you'll be looking at velocity time graphs, and I'll ask you the same questions on both. How far does it go? How fast is it moving? And so you want to know which approach to take depending on what that title is. So please, 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 it always breaks my heart to see students on the final answer a whole page of questions and they're thinking they're looking at a different graph, a different title of a graph than they really are. So I'll try to start you off with a few questions just to kind of get your bearings. Okay, initial velocity. Velocity is listed on that graph, so there wasn't any need to to find slope or do calculations or anything like that. So initial velocity is just up here at 6. Velocity at 3 seconds, that's right here. Velocity at 3 seconds, my velocity is 2. When is the car moving at constant velocity? Well, that's going to be when the velocity stays the same. That's going to be when it has a 0 slope here. And then when does it have negative acceleration? That's going to be this first part when the velocity is going down, when you have a negative slope. All right, so to figure out what that slope is, I just took it's rise over run, but I go, down 4 over 3. So down 4 over 3, that's the slope there. Now, to figure out how far this one goes, between 0 and 6, so not the entire 10 seconds here, just between 0 and 6, how far did it go? There's a couple of ways to solve that, but hopefully what you're thinking about is you have two distinct parts of its motion. You have a part where the acceleration is negative, and you also have a part where the acceleration is 0. If you have two different values for the acceleration, then you have to use that distance formula two separate times. So So if you like the distance formula, get your acceleration for the first few seconds, which we did, plug that in for A. Remember, your time, though, was only for the first 3 seconds. And it did, if you remember, it did have an initial velocity of 6. Keep that negative in there. That's really important. That's really what it means for these values to be vectors. All right, then for the second part where it was holding steady, the velocity was holding steady, acceleration was 0. You can still use our distance formula. Just plug in 0 for A. Now at that interval, at that 3 seconds, there was an initial velocity of 2. So make sure you use that, and once again it was only for 3 seconds. You add up the 2 and you should get the total distance. Now please, there's also the shortcut. You can find area on a velocity time graph, and that will provide the distance. So there's a lot of ways to kind of break this one up. I thought the easiest way was a little triangle up here, 1/2 base times height, and a rectangle here, which was just base times height. And I added those two sections together, and I do in fact get the same answer for the distance. All right. Now this one here, you're not given a graph, but I hope you can kind of look at how this animal is moving around and make a little sketch, make a little velocity versus time graph from what's given. So this one does say he's starting at rest, so he's sitting there. He will, over 5 seconds of time, his velocity will get up to 23. He will hold that pace for another 10 seconds for a total time of 15. So I think if you graph this out, it's easy to see I got 2 distinct parts of his motion. I could either use equations or I could use the area trick, and you should get the same answer for that. All right, the force diagram problems, the sliding block problems. The thing I'll tell you here is the steps will be there. So hopefully, and the little equations will be there. Have a very similar look when you get to take your final exam. The thing I'll say, and I think what helps the most is, I mean, even if the steps are, you got to know the weight, the force due to gravity, so that's different than the mass. Now, it does say balanced forces vertically. Balance, so pay attention to those little statements as you go through the final. That really gives you a clue how this thing's moving, what direction it's going in. The balanced forces vertically, now we got a weight. Now what's going to balance the weight is the normal force and this applied vertical force. So both of these force vectors going up will balance the weight pulling down. So be careful on this one. The normal force is a little, look at the normal force. I always like to think normal force. What would a scale read? So if you put this on the scale, this 200 Newton thing on the scale would only read 170 because you're pulling up with 30. 30 is not enough to lift it, but it certainly is enough to kind of take some of that pressure off and change what the scale would read. Now, why do we care about the normal force? Well, because that's what determines, that pressure is what determines the friction between the two materials. So we needed to know that normal force in order to figure out the frictional force. Once we figured out the frictional force, then it's easy to sum or add our horizontal forces. When you add your horizontal force, it says they're not balanced. And really what that means is I'm pulling with 52 newtons or so to the right. Friction's pulling back with 8, 9 newtons to the left. So you subtract those in order to find their net total. And once you got the total force that's going to be applied horizontally, then you divide that by the mass to get the acceleration of that object horizontally. Once you have acceleration, you can figure out how fast it was moving and how far it was going. Now, just kind of, I think this is kind of worthwhile. You were able, given that force diagram, we actually could sketch a velocity time graph. And so this is, I mean, in some ways kind of a good summary of the whole physics first semester and what mechanics is all about. But if you know the forces applied to an object, then you can figure out what happens to it. And if you wanted to make a velocity versus time graph, it started at 0. The velocity got up to about 10. So there's our velocity. And so I could find the area, and that area does indeed give us the same answer that we got for the distance when we use the distance formula. 27, a little tricky. Well, not really tricky, but when it says ignore air resistance, the mass of the object doesn't matter. Could be a golf ball, could be a tennis ball, could be a marble. It doesn't matter. So we will do some problems where we consider air drag, but we'll look at that beginning second semester. Yeah. 28. Some people look at this one. Let me see here. Okay. The way I like to think of this one, it's like you're starting it at the peak. So if you think of our projectile problems, kind of imagine I put this apple or this marble, whatever it is, I'm starting it at the peak, and it's going to drop to this bucket here, or get kicked off, or kind of. Now, this is not an off-the-table launch. So maybe some students looked at this and said, off the table. I'm like, no, it's not off the table, because I'm not launching it up. So it's not one of these really complicated ones. There is no angle here. Just wants to know how fast does it have to be pushed off of here in order to land in here. Now, since there's no up or down component to this initial velocity vector, the time it takes to fall 10 meters is the same as if it was moving horizontally and then fell 10 meters. The time is the same. So the first part is just how much time does it take to fall 10 meters? Use our distance formula. The second part then is once you know the time, and we say gravity has no effect on the horizontal component of its motion, so we could just use our very simple distance over time equation to figure out how fast it has to move horizontally. All right, then projectile problems might be good, kind of looking back over some of those notes and some of those example problems that we did. And I think what I'll do on your exam, this is really right here. This is really step 2. This was really step 3. Step 1 I didn't put on here. Step 1 was to draw a velocity vector triangle. So you have this launch speed, then you have remember how fast is it going to be scooting along horizontally, how fast would it initially start to climb. So step one was really SOHCAHTOA. Get your horizontal velocity, get your vertical velocity. Step two is use my vertical velocity. Use my vertical velocity to figure out the time. Now please remember that time only gets you halfway. All right, that's really the time from the peak to the ground. So then we would double the time, and when you doubled the time, that's the total time this thing's going to move for. And then that we would also use our horizontal velocity times the total time would give us the horizontal distance. Now remember, this one's a 45-degree angle, so that is why we would in fact expect our horizontal and vertical vectors to be the same at a 45-degree angle. Okay, and then how high up what's the distance it climbs? Well, the key on this one is just use our distance formula, but the time, make sure that the time that you use is indeed just the time to the peak. Don't use total time, because total time gets you all the way. If you use total time, you got things going up and down. Yeah, you don't want that. You just want to use that half of the time, that time to the peak. All right. Oh, the rope. Okay. Now the way I think of these ones, it's really that the vertical component, the upward force of each rope is going to take or balance half of the weight. So it becomes a pretty simple triangle problem for us if you think that this vertical force due to tension, that vertical component, is in fact going to be half of the weight. So this 28 kilogram object, this 28 kilogram mass, weighs 280 newtons. The vertical component of the force would be half of that, And then once you got that upward force of 140, it's pretty easy to find the hypotenuse, to find the force due to tension for the actual string, the actual rope. Cart crossing the reference point. Be careful on these because there is an initial velocity. The initial velocity is, in fact, 3. So there is an initial velocity. So be aware of that. It does speed up as it moves, so there is some acceleration over time as well. That should say meters per second, mistake there. And then once you got that acceleration, you can use that for our distance formula. Remember, there was an initial velocity. Now, the other thing, if you know the average velocity for the whole journey, you can also use that to figure out the distance. So generally we say velocity is distance over time. If you really know what that average velocity is for the entire interval, then indeed you can average it out and then also find the distance that way. So, okay. It's kind of more evidence of why our distance formula works, I guess, or where it came from, I guess. So these ones on the, we'll say these initial velocity to launch, to jump, these hang time problems, what it will say on your final exam is I will say, I believe it says something like, determine the speed needed to launch a marble 75 centimeters in the air, or something like that. So my best advice for you on these is, and if you think of the day even when we would kind of shoot marbles up and take a picture of how high up it got on the ruler, solve it as free fall. So the distance it climbs is the distance it climbs is the same as the distance it falls. So just start it at the top. That way we got gravity as a positive value coming down, the distance positive value coming down, and you can figure out how much time it takes to fall back to its original spot. And then once you know that, you can figure out how fast it would be going right when it fell that far. And that speed it was going right as it fell that distance is going to equal the speed you would need to launch it up to that distance. So that's what's going on there. So when I say initial velocity, I think what I'll say on the final is the speed needed to launch a marble this high in the air. And that times that kind of makes a little bit more sense to students. I hope you're doing well with conversions. Maybe it's been a little while. Haven't asked you to do one on a quiz in the last couple months, but or a month or so. But anyway, the key thing on these is I just can take this time, 7 minutes. You can either change it to total minutes, like 7 1/3 minutes is what that is. A lot of students also can change it to total seconds. So either way. But just start with your total distance and your total time, and then divide it by 1609. And then if it's minutes, multiply by 60. If it's seconds, multiply by 3600 for seconds in an hour. Yeah, back to these. This was kind of our very first introduction to triangle problems and vector addition. But it also kind of gets at what's the difference between velocity as a vector, really what we're looking at then here is this velocity takes into account your displacement from your start to your finish on a direct line. Where the word speed really just kind of says how far did you go. It doesn't really matter what direction you're moving in or anything like that. So this total distance this baby crawled was 24 meters, but they were technically only displaced about 16, 17 meters. The two lab cars moving at each other. The shortcut here on this one, and in fact, first of all, the negative, that should say meters. That's another mistake, I'm sorry. That should say meters per second, not centimeters. And the negative is just there to let you know that the cars are moving in opposite directions. But when you go to solve, really you can set up one car moving one way, the other car moving the other way. You don't need the negative in there to solve it. Now, the shortcut, and I think a lot of students are recognizing this, the easiest way to do this is to think these two velocities added together So 0.12 plus 0.3, those two velocities added together, multiplied by the time they move, will equal the total distance. So the total velocities added together, multiplied by the time, is going to equal the total distance they cover, the total distance each car covers together. So that is an easy way, I think, to figure out what the time is. And once you know the time, then then you just multiply it by the velocity to figure out how far they go. And a great way to check yourself is the distance each car moves should equal the total distance between them at the beginning. Okay, position versus time. So if this is a position versus time graph, and I ask you for a velocity, you're going to have to find slope. And just count, just rise over run. And for the second part, I think rise over run, I go, what, down 6 over 4. So it's not the same, it's not symmetrical. So not the same slope on each part. Now, the overall average velocity on this, think about it, did they really go anywhere? It's like think about, this is like someone got up in the classroom, they walked 6 meters away, they wanted to grab a pencil or something, or get a piece of paper from another desk, and then they walked a little more slowly back to their original spot. So they started and stopped in the same position. Their displacement was 0. Their overall average velocity then would be 0. Now the speed, though, keep in mind, the speed takes into account total distance. So if I walked 6 meters up and then turned around and walked another 6 meters back, I actually covered a total distance of 12 meters. Some people kind of think of that as like, if I was wearing my Fitbit, how many total steps or how many total distance would I actually cover? All right, okay, so velocity versus time. Velocity. So this one is showing me how fast something. Now look at this. This velocity starts negative, gets to 0, and then it becomes more positive. This is like pushing our cars up and down the ramp, where they would slow down, slow down, slow down, slow down, stop, and then speed up, speed up, speed up. Why can something change direction and just have one line on the velocity time graph? It's because it is a constant acceleration. It's acceleration due to gravity and also based on that incline of the ramp. But this is just pushing a car up the hill. It stops, and then it's going to speed up as it rolls back down the hill. So find the accelerations. Now, a good hint on this is if this is one line, that really is one value. It's the same acceleration the whole time. So it's kind of like goes back to those questions like throwing a ball up in the air. Up or down is the positive direction. This would be throwing a ball up in the air. Down is the positive direction. The ball slows down, slows down, slows down. It stops, velocity of 0, and then it speeds up, speeds up, speeds up as it falls back down. And your acceleration would be the same at any point while it's moving. And once again, if you know the acceleration, you could figure out distance and all that other good stuff. But I like this little handwritten one at the end. At what time did the car stop and change direction? Well, that was when it stops when the velocity was 0. And that was at the 3-second mark. And like I said, just think of that as the car rolling up and down the ramp. Well, good luck on this final. Thank you so much. I really enjoyed our first semester on mechanics. I hope you have a good, my goals are that you can use kinematics equations very effectively for any scenario. You can interpret graphs in a meaningful way. And you also have kind of an understanding of how gravity does impact all of these forces that are applied to an object, which starts to affect how it's really going to move around. Thanks for your time. Good luck.